I saw the light. And it turns out it was X-rays, and they burned my eyes, and I was damaged forever. Oh no! Well, anyway, sorry. Strange beginning to the video here. Let's talk about talk about light some more. So we left off last time just on a general discussion of waves and how wavelength and frequency are related to each other. We're going to talk a little bit more specifically now about the different kinds of, well, I shouldn't say kinds, the different regions of the electromagnetic spectrum. So if we look at our graphic here, we have on this end very, very high frequency light with very, very tiny wavelengths, because again, those are inversely proportional. So as the frequency increases, the wavelength decreases. Gamma rays and X-rays down here at the bottom end of the spectrum are extremely energetic light. So energetic that they will damage you. UV is actually can damage biological tissue as well. Not quite as badly, though. These just give you sunburns. These will ionize your DNA, so it's a bit different. But the gamma rays, X-rays, and UV, those are high energy light, high frequency, low wavelength, or small wavelength. Right next to UV, we have visible light, and purple is the highest energy visible light. We're used to hearing about, blue light and needing blue light filters. We need purple filtering as well, because the purple is actually higher energy than the blue light is. And then red is the least energetic of the visible light, because the higher frequencies give us higher energies, which I believe we will talk about a little bit more in just a second as well. And then as we keep going to lower frequencies, larger wavelengths, we get to infrared, that is IR radiation, microwave radiation, and yes, indeed, that is the same microwave radiation that is used in your microwave in your kitchen. We have radio waves from pretty much this point on. So all of these are kind of different regions, but they're all called radio waves. So we have FM and AM radio waves that we use to listen to our tunes and the news. And then we have long radio waves, which are, I wouldn't go so far as to say useless, but they're not as useful as the shorter radio waves, mainly because you need fancier and fancier antenna to be able to pick up these really long radio waves. Because usually the size of your antenna has to be on the same order as the wavelength of the light that you're trying to detect. And so with the really long radio waves, where we have excessively long wavelengths, it just gets really difficult to measure those. This, by the way, is also one of the reasons why we had so much trouble detecting gravity waves. If you've heard about those, they haven't been in the news for very long. They haven't been in the news for a while. They were in the news for a while a year or two ago. But one of the reasons we had a hard time detecting gravity waves is just their wavelengths are excessively long, and so we had to set up a detector that was essentially the size of the planet. And that's not an exaggeration. Like, we had multiple detectors set up at different points on the planet that essentially each worked as a different part of one detector. So they all worked in concert with one another. And so working together, they were able to detect gravity waves. I'm pretty sure they detected a gravity wave. At least I know that for sure they were meant to detect a gravity wave. But they needed something that was a detector the size of the planet in order to be able to do that, because the wavelength was just so insanely long. But anyway, moving on, if we are interested in talking about these different kinds of light and talking about the wavelength of the light and the frequency of the light, it is often going to be necessary to be able to convert between those two things, between the wavelength and the frequency of the light that we're interested in. And to do that, we are going to use this equation. And I know that looks like Greek. It's because it is. The C is not Greek, but these two are both Greek letters. And what this equation tells us is that the speed of light which is c, is equal to the wavelength, which is a Greek letter lambda, I believe that's what that is, times the frequency. And I believe that is the Greek letter nu. But you can correct me if I'm wrong about that. So the speed of light is equal to the wavelength times the frequency. It's a pretty straightforward equation. Shouldn't give us too much trouble. The one thing that's going to give us trouble, though, that we're going to have to watch out for at least, is the units. The units can sometimes be a pain in the neck. But other than that, it is a pretty straightforward equation. So let's do an example here. We're told that red light has a wavelength of 700 nanometers, and we're asked to find the frequency of that light. All right, so you're trying to find nu, trying to find the frequency. I would like you to go ahead and pause the video, if you are willing, and try to work that out yourself before we do it together. Okay, so we're told that the wavelength is 700 nanometers. We know we can use this equation to find frequency. We also know that c is 3 times 10 to the 8 meters per second. So, if we go ahead and do the algebra here first, if we're trying to find nu, we can divide both sides by lambda, which will give us frequency is equal to the speed of light divided by the wavelength. And if we just plug in what we're given, what you might notice is that we're given both of these things, but this is in meters, this is in nanometers. We need those both to be in the same unit, and oops, what did I pick? Oops, I do not want a highlighter, I want an eraser. There we go. I want them both to be in meters, not nanometers. Just personal preference. You could technically have them both be in nanometers. You're just going to be dealing with a lot more scientific notation, or at least this is going to end up being a absolutely huge number. I prefer to go ahead and switch this to meters, because all we have to do is that. Sorry, my M looks a little weird there, but nano stands for 1/billionth, which is 10 to the negative 9. And so all we have to do is just remove the nano and put in times 10 to the negative 9. And we have our value in meters. And I think that's a lot easier than converting the meters per second into nanometers per second. Okay, so if we do the math there, and this is another one of those examples where it's very important that you use the engineering exponent, because you're going to get a very wrong answer if you just do times 10 raised to without parentheses. It's going to give you really wacky numbers. So with the correct numbers there, the frequency of red light is 4.28 times 10 to the 14 1/seconds, which is sometimes phrased per second, and also sometimes phrased hertz. So a hertz is a cycles per second, and so it's 3 different names for the same thing, essentially. It's just reciprocal seconds. All right, let's do something similar here. Now with violet light, this says violet light has a frequency of 7.54 times 10 to the 14 per second. S to the negative 1 is 1/seconds. Now we're asked to find the wavelength. Okay, we can do this as well. Again, I would encourage you to pause the video here to work this out yourself if you would like to see if you're grasping how to use the equation. So now we are trying to find wavelength, and so instead of using this equation, we're going to divide both sides by the frequency, and so that will give us the wavelength is equal to the speed of light divided by the frequency. We are given everything that we need to solve this here, and we don't even have to do a unit change in this case, because we know 3 times 10 to the 8 meters per second is the speed of light, and we are told that 7.54 times 10 to the 14 per second is the frequency. And so if we do that math, 5 by 7.54 times 10 to the 14, the wavelength of this light is 3.98 times 10 to the negative 7 meters. It doesn't specifically ask for this, but I'm going to go ahead and convert it to nanometers. That would be 398 nanometers. And you would get that, by the way, by dividing by 1 times 10 to the negative 9. That would give you the wavelength in nanometers. Okay, let's do at least one more here. So this question asks us, what color is light that has a frequency of 5.88 times 10 to the 14 per second? And we're going to have to go back and use the graphic from the previous slide to figure that out. But before we can do that, well, actually, not before. Let's just go ahead and look at it. If you notice here on this graphic, we're not given frequencies for the different colors. We're only given wavelengths. So we're going to have to convert this frequency into a wavelength, just like we did a minute ago. Well, probably not even a minute ago, 30 seconds ago. So we're going to do the exact same thing here. Speed of light has not changed. The frequency is different, though. So we have the speed of light divided by 5.88 times 10 to the 14. And if we plug that into our calculators, that is going to give us 5.1 times 10 to the negative 7 meters, which would be 510 nanometers. And so if we go back and we look, 500 is right here. There are 10 marks here between them. And so this would be 510. So that would be green. This is green light. Which, by the way, green is my favorite color. So for some reason, my brain likes 510 nanometer light. It's pretty great. So, there are more examples in the book, although that example number is not correct. That's from an older book. But there are more examples of converting from frequency to wavelength that you can do from the book. So I'd encourage you to do that if you're still having issues with understanding how to convert between those two. I think we'll call it here for this video. In the next one, we will start to talk about interference and constructive versus destructive interference, where we have waves in and out of phase with one another. And I know that sounds like a really Star Trek thing. It's in phase or out of phase. It's really not. So we'll talk more about that in the next video.